Hello and welcome back to part 3 of chapter 9. We're going to start off with section 9.4, the significance level. So as we said, the smaller and smaller p-value provides stronger and stronger evidence against the null hypothesis. Although it is unwise to draw firm cutoffs, here are conventions that are used as a starting point. So as we said earlier, if we had a p-value, let's say of we had one earlier p-value equaling 0.27. That's a very high p-value, and one that's, as you can see, p-value is greater than 0.10. We would say this is non-significant evidence against the null hypothesis. See, 0.27 is very high. But if we say we had a p-value of a p-value equaling 0.02, well, this one we would say, is right here. It's between 0.01 and 0.05. Which we would say there's significant evidence against the null hypothesis. So in a situation like this, as long as our alpha level, which alpha level is normally set at, for most studies, at 0.05, as long as our alpha level of 0.05 is set here and our p-value is 0.02, we reject the null hypothesis, and we would say this is significant evidence against the null hypothesis. If it was greater than 5, but less than 10, we would say there's marginally significant evidence against the null hypothesis. And depending on where you set your alpha level at, we may or may not, we either may reject a null hypothesis or fail to reject a null hypothesis. It's very rare you'll see an alpha level at 0.10 or 10. Most of the time you'll see it at 0.05 or less, but you can see it at 0.10. And that only provides marginally significant evidence against the null hypothesis, which in turn, you don't see very often. Now, if you did have a p-value of 0.01, the very last one, a p-value of less than 0.01 is highly significant evidence against the null hypothesis. You can see sometimes alpha levels at equaling 0.01, and this is highly significant evidence against the null hypothesis. So, like we said, here's an example. Our example p-value 0.27 is non-significant against the null hypothesis, and a p-value of 0.01 is highly significant against a null hypothesis. So decision based on alpha level. So alpha represents the probability of erroneous rejection of a null hypothesis. Alpha is represented by this little symbol, Greek symbol here, alpha, and normally you state an alpha level prior to beginning any kind of research. You set alpha threshold for acceptable error, so you let alpha equal 0.10 or let alpha 0.05, whatever level is acceptable. Like I said, the majority of the time in research you'll see an alpha level equals 0.05 or less. You'll very rarely see it at 0.10. You reject the null hypothesis when your p-value is less than alpha. So an example, if an alpha level is set at 0.10 and you find a p-value of 0.20, since p is greater than alpha, you retain the null hypothesis and you failed to reject it. However, if you set an alpha level at 0.05 and find a p-value of 0.01, since p is less than alpha, you reject the null hypothesis. One sample z-test condition. So some conditions that should be met anytime you're doing sample collection and running a z-test is you want quantitative responses. It's not going to work very well if you have qualitative responses. Good data, remember garbage in, garbage out. You want an SRS, you want a known standard deviation. If you don't know it, we'll go over what you do if you don't know standard deviation later in the book, but you want a known standard deviation of the population. Population is approximately normal or a large enough sample size. This is we'll get to a little bit later, but we've kind of touched on it in the central limit theorem. If you take two different samples and over time, on a small end of a graph, let's say from 0 to infinity, if you take 10 people, you could have a value here somewhere, 20 here, 30 here, and you're not really sure what the actual true value is. And so you have another sample and it goes like this and goes like this. You could be all over the place. But as technically, as the central limit theorem states, as you increase your n, increase the sample size, you get closer and closer to the actual true value of what you're looking at, and this is the population approximately normal. So as long as you're not studying some sort of like rare disease or some area of science that there's not a lot of known information, the central limit theorem normally applies. So one sample z-test procedures. Remember, we state our null alternative hypothesis, where our null hypothesis is going to be mu equals the mu of the null hypothesis, and then you're going to state the alternative hypothesis. You're either going to say it doesn't equal, which is a two-sided, or you're going to say it's greater than or less than, as the left-sided or right-sided example. Then you're going to use your test statistic, which right here we use our z-stat test, which is our x bar minus our, this should be the mu of subset 0, so our null hypothesis, so x bar minus our null hypothesis over our standard error of x, where remember standard error of x equals the standard deviation over the square root of n. Then once we find that, we will find the p-value that corresponds to it. You can either use a graphing calculator, your table B, or other software to do it. And then depending on where your p-value is, you'll state it compared to the significance level of alpha. So here's an example of the Lake Wobegon problem. So typically, an adult intelligence scores are normal, have a normal distribution with a mean of 100 and standard deviation of 15. So we're going to take a simple random sample of 9 people from Lake Wobegon here, and these are their intelligence scores that they scored on the exam. This is your data set. If you were to add them all up, divide by 9, you'll find that you calculate your x bar as 112.8. So does the sample mean provide statistical reliable evidence that the population mean is greater than 100? So here we're going to run our hypothesis testing. So we state our null hypothesis, which is mu is equal to 100. Our alternative hypothesis we're going to state is mu is going to be greater than 100 one-sided. So here we set up our test statistic. First, figure out our standard error of x, which remember is the standard deviation over the square root of n. So 15 over the square root of 9 equals 5. Then we calculate our z-stat, which is going to equal our x bar, which we calculated at 112.8, minus our mu 0, mu of our null hypothesis, over the standard error of x, which is 128 minus 100 over 5, and we get a z-stat value of 2.56. If you go to 2.56 in your book, remember if you go to actually the z-tenths 2.5 and then go over and find 0.06, you will find that the value corresponding to that in our table is 0.9948. And when we calculate the p-value, it's 1 minus that, right? Because that's telling us, the 9948 is telling us in the book at that value and everything to the left. And our p-value is the one we want to the right of it. So 1 minus that, and we get our 0.0052 from table B, which 0.0052 is highly significant evidence against the null hypothesis. Remember, even if we set an alpha level for this example equaling 0.01, 0.0052 is less than 0.01, so this is highly significant evidence against null hypothesis. We would reject the null hypothesis at this point. So the significant level, this level of evidence is significant even at alpha level 0.01, and you reject the null hypothesis. For a two-sided p-value in the Lake Wobegon illustrated example, so we set this, our null hypothesis is the same thing, where our mu is going to equal the 100. Alternative hypothesis is mu does not equal 100. We already do the exact same steps because we already figured out the mean and our z-stat value. The only thing we do different here is we find, once you get your p-value of 0.0052, you multiply it by 2, and you get 0.0104, which still provides significant evidence against the null hypothesis. So here's an illustrated example of the two-sided hypothesis. Remember, on one-sided, this is where we are. We multiply by 2 because the bar here is symmetrical, and you see the exact same thing on this side, and this is how we calculate it in an illustrated example. The next part of this chapter goes into power and sample size, and I will do that in another video, and I will see you all then.